Welcome to AI Paper Podcasts. Today we are looking at a really fascinating one. It's called Unified Latents, or UL, How to Train Your Latents.
Yeah, this is by Jonathan Heek and the team at Google DeepMind over in Amsterdam.
And we're just going to get right into it. The core problem they're tackling here is that classic, honestly really painful trade-off in generative models, like stable diffusion.
Right, the seesaw between latent information density and generation quality.
Exactly. Usually, if you make your latents easy to learn, you get really bad reconstruction. But if you demand perfect reconstruction, the latent becomes, impossible to model.
And their solution here is a framework they call unified latents. They essentially co-train a diffusion prior right on the latents themselves.
Which is super clever. They link the encoder's output noise directly to the prior's minimum noise level.
And the results they got are, they're serious. On ImageNet 512, they hit a really competitive FID of 1.4.
But the video performance is what really caught my eye. They set a new state-of-the-art FVD of 1.3 on Kinetic's 600.
Yeah, and they did all of this while requiring fewer training FLOPs than models trained on your standard stable diffusion latents.
So for you listening, the so what here is that UL provides this tight, interpretable upper bound on latent bitrate. And you don't have to do that awful manual tuning of KL penalties anymore.
No more magic numbers.
No more magic numbers. So that's the summary. Let's really get into the context here, because to appreciate what DeepMind did, we have to look at the landscape of latent diffusion models right now.
Right, the heavy hitters. We all know models like stable diffusion. They don't generate pixels directly.
Right. They generate a compressed latent representation.
Because scaling diffusion models to high resolutions directly in pixel space it's incredibly expensive computationally.
Yeah, you'd burn through your whole compute budget just trying to generate a tiny image.
Exactly. So you compress the image down into a smaller latent space, do all your heavy diffusion magic there, and then decode it back to pixels. It's completely standard practice.
But, and here is the friction point that pretty much every ML engineer hates. How do you actually train that compressor, that autoencoder?
Well, the standard approach, the one used in the original latent diffusion paper, uses a VAE-style KL penalty.
Right, a Kullback-Leibler divergence penalty. So you have an encoder that outputs a distribution, right?
Yeah, and you want that distribution to look like a standard Gaussian so the diffusion model can handle it later. So you slap a KL penalty on it to force it into that shape.
But the problem is the decoder in these models typically lacks a likelihood-based loss.
Right. It's usually just trying to reconstruct the image pixels using an L1 or L2 loss.
So you end up with these two completely opposing forces fighting each other.
The reconstruction loss wants to pack every single high-frequency detail into the latent. It wants this jagged, incredibly complex map.
And the KL penalty wants to smooth everything out into boring, uniform Gaussian noise.
And the engineer is just stuck in the middle, manually tweaking the weight of that KL term.
It's totally a guessing game.
It really is the magic number problem. If you set that weight too high, you get what we call scenario A.
Which is low information density. The latents are super heavily regularized.
Yeah, they're basically just noise, which makes them very easy for the diffusion model to learn. You get a great FID score. The generated images look like real images.
Well, if the reconstruction is terrible, you get horrible PSNR.
Exactly. That's when you lose the texture of the grass or the grain of the wood in the background. The image looks fine at a glance, but it's fundamentally not the image you actually encoded.
Right. But then if you go the other way, scenario B, and you lower that KL weight B,
then you get high information density. You get near perfect reconstruction.
But now the latent space is this complex, spiky manifold that the diffusion model just completely struggles to learn.
Yeah, you'd need massive, massive modeling capacity just to figure out how to generate those latents.
So it's a seesaw. You push one side down, the other goes up. And until this paper, we've mostly just been tweaking the fulcrum by eye, just guessing what looks best.
Which is not very scientific.
Yeah. No, not at all. So the goal of unified latents is to stop guessing and systematically navigate this trade-off.
And their framework basically relies on three pillars: a deterministic encoder, a diffusion prior, and a diffusion decoder.
Let's start with that encoder because this stood out to me immediately. Standard VAEs predict a distribution, a mean, and a variance. But DeepMind is saying, no, just give me a single point.
It's a really crucial simplification. Standard VAEs Learning that variance is notoriously unstable.
Yeah, it often collapses, or the model just learns to game the variance to minimize the loss.
Exactly. So DeepMind just bypasses all of that. The encoder is entirely deterministic. It predicts a single, clean, latent value. Let's just call it Z-clean.
But wait, if it's deterministic, where's the regularization coming from? If you don't add some kind of noise, the model just memorizes the training data, and you have zero smoothness in the latent space.
And that is the link we mentioned in the intro. They take that deterministic output, that Z-clean, and they explicitly add a fixed amount of Gaussian noise to it.
Right, they noise it forward to time t equals 0 with a final log SNR of 5.
Yes.
So log SNR of 5, for those of you doing the mental math at home, that corresponds to adding fixed noise with a standard deviation of about 0.08.
Roughly, yeah. So it's a very small fixed amount of noise. But here is the major architectural shift. This specific noise level becomes the absolute maximum precision of the prior diffusion model.
Oh, so they aren't just adding noise randomly to regularize, they are perfectly aligning the encoder's output with the starting point of the prior.
Precisely. So the prior models, the path from pure noise, which we can call Z1, all the way down to this slightly noisy latent Z0.
And because they mathematically align those noise levels, that old KL term, that awful magic number we had to weigh manually, it just reduces down to a simple weighted MSE over noise levels.
It just becomes a standard diffusion objective.
That is so elegant. So the prior handles the distribution of the latents, and the decoder handles the reconstruction from the latent to the image.
Yes, and they use very different loss weightings for each, which is super important to understand. For the prior, they use an unweighted ELBO loss.
Unweighted ELBO. Okay, why is that key?
Because it forces the model to treat every single bit of information equally. It ensures the encoder can't hide information in noise levels that the model decides to discount.
Ah, I see. Because if you discounted the noise in the prior, the encoder would just stuff all the really hard-to-model data into those discounted regions just to cheat the loss function.
Exactly. The encoder's lazy. It'll find any loophole. The unweighted ELBO bounds the information rigorously. But for the decoder, they do use a reweighted ELBO, specifically a sigmoid weighting.
Why the difference? Why unweighted for the prior, but sigmoid for the decoder?
Well, the decoder's job is perceptual. We know humans aren't sensitive to pixel-perfect noise at super high frequencies.
Right, we can't see imperceptible grain.
So by using a sigmoid weighting in the decoder, they allow the model to focus on the visually important features, things like edges, shapes, colors. And it can safely discount the high-frequency noise we can't see anyway.
Okay, so let's visualize this whole pipeline for the listener. You take an image, the encoder turns it into a clean latent.
Yep.
You add that fixed standard deviation of 0.08 noise to get Z0.
Right.
Then the decoder tries to turn that Z0 back into the image, and simultaneously you have this separate prior model learning how to generate that exact Z0 starting from pure static noise.
That is the unified latents architecture in a nutshell. It takes the black box of the latent space and turns it into a totally transparent, predictable communication channel.
Having that architecture makes total sense, but training 3 separate networks all dancing together seems like it would be a nightmare.
It could be, but they employ this 2-stage training process, which is actually quite clever.
Okay, break that down. Stage 1.
In stage 1, they train the encoder, the prior, and the decoder all jointly. This is where they establish that strict information bound we just talked about.
Right, but they make a point in the paper that the prior trained in stage 1 isn't actually the one you want to use for generating final samples.
Correct. Remember, the stage 1 prior uses that unweighted ELBO to rigorously bound the information. But unweighted ELBO is famously terrible for visual sample quality.
Because it spends way too much capacity trying to model invisible high-frequency noise instead of the actual structure of the image.
Exactly. So once stage 1 is done and the latent space is well defined, they freeze the encoder and the decoder entirely.
And we enter stage 2.
Right. In stage 2, they take a fresh model, or they just retrain the prior, and they treat it as a base model.
And this time they train it differently.
Yes, they train it on those now fixed latents, using that sigmoid weighting we mentioned. So now the prior prioritizes visual quality over strict information bounding.
And this base model from stage 2 is what actually generates the images when you deploy the thing. So to use an analogy, stage 1 builds the road. It defines the latent space and makes sure it goes to the right destination.
I like that.
And then stage 2 builds the car that actually drives on that specific road.
That's a great way to think about it. And because the latent space, the road, is already fixed and well behaved, that stage 2 training is incredibly efficient. You aren't chasing a moving target anymore.
That makes a lot of sense. Now, they promise no magic numbers, but let's be real, there are still hyperparameters in this framework, right? We haven't completely escaped
You
tuning.
never completely escape tuning. But the difference is these knobs are interpretable. Instead of an arbitrary KL weight, they give you a loss factor, which they call CLF, and a sigmoid bias B on the decoder.
Okay, so how do I actually use those knobs? If I'm training a model, what does tweaking the loss factor do?
Essentially, if you upweight the decoder loss by increasing that loss factor, you are forcing the system to prioritize reconstruction above all else.
You're telling the model, I don't care if this latent is a nightmare to model. I need the output pixels to match the input pixels perfectly.
Right. So a higher loss factor equals a higher latent bitrate.
And higher bitrate gives you better reconstruction, which means a better RFID score. But it makes the latent much harder for the base model to generate from scratch.
Exactly, which leads to a potential drop in generation quality, your GFID, especially if your base model isn't very large.
And that is the so what of the whole trade-off. It's systematized now. And they found that typically a loss factor between 1.3 and 1.7 is kind of the sweet spot.
It is. And interestingly, they note that larger base models are much less sensitive to this.
Oh, really?
Yeah, if you have a massive generator, you can just crank up the loss factor, pack tons of info into the latent, and the large model just has the raw capacity to handle that complex distribution.
Small models, however, just crumble if the bitrate gets too high.
Exactly. They just can't fit the curve.
Well, going back to the car analogy, a Ferrari can handle a much rougher, more complex road than a go-kart can.
Perfect analogy. It basically allows you to perfectly match your latent density to whatever your actual compute budget is.
Let's look at the scoreboard. They ran a ton of experiments to prove this out. Let's start with ImageNet 512.
The gold standard benchmark. They plotted the training cost in zettaflops against the generation quality, the FID, and unified latents consistently outperformed the baselines.
We're talking beating DT-XL2, CD2, and the various stable diffusion baselines.
Handily. Basically, for every unit of compute you spend, UL just gets you a strictly better image. Or you can get the exact same quality for way less compute.
They also explore the architecture of the autoencoder itself. They use 2x2 patching to save compute.
Right, which is pretty standard now in vision transformers. You just treat small grids of pixels as a single vector.
But they found a really interesting nuance here. Patching actually hurt the base model performance compared to using traditional convolution stacks.
Yeah, the patches introduce a kind of jaggedness or high-frequency grid artifact that makes the diffusion task slightly harder for the prior.
But they kept the patching in the final recipe.
They did.
Yeah.
Because the computational savings of patching were just so massive that UL still won on the overall efficiency chart, even with the slight performance hit.
That's a good warning for researchers, though. Patching isn't a free lunch. It comes with a modeling cost you have to pay down the line.
Highly efficient, but slightly more difficult to model.
What about the latent channels? Like, how wide does this information pipe need to be?
They did a full sweep, varying it from 4 channels all the way up to 64. And surprisingly, the model is very insensitive to channel count once you hit a certain threshold.
And what was the sweet spot?
32 channels.
The 4 channels was too low.
Oh yeah, at 4 or 8 channels, the bottleneck is just physically too tight.
Yeah.
The encoder cannot pass enough information through to get good reconstruction, no matter how much you crank up the loss weight.
Now, the part of the paper that really caught my eye, and we teased this in the intro, was the video generation on Kinetic 600.
Video is the ultimate stress test.
It really is, because you aren't just reconstructing spatial details, you are reconstructing time.
And temporal consistency is the absolute killer in generative video.
Yeah.
So they used a setup with 4x8x8 downsampling. They conditioned on 5 frames to generate the next 11.
And the result was that crazy state-of-the-art FED of 1.3.
1.3 is just an incredibly low score. It outperformed Google's own video diffusion models, MangVIT V2 WALT.
Which suggests that this unified latent approach is particularly potent for video.
Totally. In video, the trade-off between temporal consistency and individual frame quality is extreme.
Yeah.
If your latents are unstable even slightly, your video flickers and warps. UL seems to solve that underlying stability problem.
They also tested this on text-to-image with an internal dataset, right? Comparing it to pixel diffusion and standard stable diffusion latents.
They did, and they found that UL, using a loss factor of 1.5, had significantly better CLIP scores.
Meaning the generated images actually matched the text prompts much better.
Right, and it had significantly better GFID than the stable diffusion latents. It was basically a clean sweep across all the modalities they tested.
A clean sweep indeed. But As always, in these heavy technical papers, the ablation section is where the real learning happens. This is where they break their own model to see why it actually worked.
The ablations here are super educational. First, they tried removing the prior gradients during stage 1.
Okay, so they put a stop gradient there and just tried to regularize the latent to a standard normal distribution, just like a standard LDM does.
Yeah, essentially ignoring the unified part of unified latents and treating it like a standard regularized bottleneck.
And what happened?
Absolute disaster. The FID jumped to 7.80.
Wow.
It proves that the learned prior is totally essential. You cannot just force the latent to be a Gaussian. You have to let the prior actually learn the latent's true complex distribution.
Okay, then they tried messing with that noise level. Remember we talked about the log SNR of 5? They tried setting it to 10.
Which implies almost zero noise, a standard deviation of about 0.007.
And reconstruction completely collapsed. The RFID went up to 28.27.
Which feels super counterintuitive at first.
Right. If the noise is lower, shouldn't reconstruction be easier? You have a much cleaner signal coming from the encoder.
You would definitely think so. But if the noise is too low, the prior fails to actually model the bitrate accurately.
The encoder realizes it can pass tiny microinformation without penalty because the prior can't see those tiny differences.
Exactly. The mathematical connection between the prior and the decoder just breaks down. That specific noise injection at standard deviation, 0.08, acts as the handshake protocol between the two networks.
So if you whisper too quietly, if there's too little noise, the prior literally just can't hear you.
That is a brilliant way to put it. You need enough noise to establish the communication channel in the first place.
And finally, they tried the old guard approach, letting the encoder learn the variance itself, traditional VAE style.
And it was totally unstable. The learned noise just dropped to 0 over time.
The model tried to become deterministic on its own, but it failed to regularize properly while doing it.
Right. They conclude that the fixed noise strategy they use in UL is a, quote, useful simplification. It removes a moving part that usually just causes chaos during training.
They also tried training everything end-to-end in one single stage, right? Skipping that whole base model retraining step we talked about.
They did. I mean, why do the two-stage thing if you could just train it all at once?
Exactly.
Did it work?
Technically, yes, it works. They got an FID of about 4.0.
But compared to the 1.4 they get with the two-stage approach, that's really not competitive at all.
No, the unweighted ELBO in stage 1 just doesn't prioritize perceptual quality nearly enough for a final product. You really, really need that second stage to polish the visuals with the sigmoid weighting.
So, synthesizing all of this for the listener, what is the big takeaway for someone who is actively building or fine-tuning these models right now? I think the biggest takeaway is that we can finally stop treating the latent space as this mysterious black box that we just cross our fingers and hope works if we tune the KL weight enough.
Right. Unified latents turns the latent space into a formal mathematical communication channel with a specific, completely trainable bitrate.
It turns alchemy into chemistry. You have actual formulas and bounds now.
You can explicitly trade off reconstruction fidelity for generation cost.
Exactly. If you have a massive compute cluster for generation, you can increase the bitrate using the loss factor. Get perfect images. If you need a fast, lightweight model for a phone, you lower it.
And you do this via a calculated parameter, not by guessing a regularization weight and waiting 2 weeks to see if it worked.
The authors actually mentioned in the discussion section that this framework is ready for scaling laws analysis.
Oh, that's huge. Just like we have scaling laws for LLMs where we can predict performance based on parameter count and tokens.
Yes. We should be able to predict the absolute optimal latent bitrate for any given compute budget. That is the obvious next step.
Imagine knowing exactly how dense your latent needs to be before you even spin up your GPUs.
It's going to save so much money.
I want to leave listeners with a thought here before we wrap up. This paper focuses heavily on images and video, continuous data.
Right.
But the core concept here, using a diffusion prior to define the valid states of a compressed representation, it seems universal.
It really does. It feels like a fundamental shift in how we think about compression for generative models generally.
So if UL allows us to perfectly tune the information density of a latent space, could we eventually use this for discrete data?
Like text.
Exactly. Could we compress entire paragraphs of text into unified latents and then use diffusion-based LLMs to generate text, not token by agonizing token, but concept by concept?
That is the holy grail right now. We know diffusion for text is struggling to beat autoregressive transformers.
It's just too discrete.
Right. But perhaps that's because we're trying to diffuse discrete tokens directly. If we could diffuse unified text latents instead, we might actually solve the long-range coherence problem in LLMs.
A really fascinating possibility to mull over. That is all for this deep dive into unified latents.
Keep optimizing those lower bounds.